Lesson 4. So this is the other piece of Unit 7. The first 3, which is your quiz is majority on, is just solving trig equations. Okay? This part now, we're switching into identities. Okay? So we went from equation to identities. And so identities are kind of proofs through the relationships of sine, cosine, tangents, etc. We're going to prove a couple and use just look at a couple and how these relationships happen. But anyways, equations and identities. In mathematics, it's important to understand the difference between an equation and identity. Like 2x squared plus 3 equals 11, that's obviously an equation because it has an equal sign, right? That's kind of what's throwing things out. It has a certain value. The solution to this equation are -2 and 2, which can be verified by substituting these values in. X plus 1 squared equals x squared plus 2x plus 1 is an identity. So what's weird about that, or different about that, is that if you try to solve these, you actually, everything would cancel. Because what they're saying is x plus 1 squared is equivalent to x squared plus 2x plus 1, like if I FOILed it out. It's writing it differently. And that's what trig identities do. You may see something, and they say, hey, make it look like this. And you have to use identities to simplify it so it would look like this. So, I mean, this is a very basic example. But if I said, make your x plus 1 squared prove that it's that, what would you do? You would FOIL it out and show me it was the same thing. Okay? That's kind of what we do with trig identities. Okay? It says, hey, you have tangent. Make tangent look like sine over cosine. Well, we know tangent sine over cosine. It's y over x, right? So that's kind of the real basic one, but we're going to go through some of this stuff, okay? So reviewing identities. So review your ratios are big for this, okay? Understand your ratios of sine, tangent, cotangent, all that stuff is very helpful. So you got your basic identities of sine, y over r, cos theta, x over r, tan, y over x, and then obviously our circle of x squared plus y squared equals r squared, which comes from Pythagorean theorem. Okay, these are reviews, so you should just be highlighting them or make sure you remember. Then again, cosecant x is 1 over sine, so that would be r over y. Secant x is 1 over cosine, so that would be r over x. Cotangent is 1 over tan, so that would be x over y. Okay, so we can use the basic reciprocals of trig identities to prove quotient and Pythagorean identities. Before doing this, we'll verify some identities in each particular case. So let's look at the first one here. So to verify, when you're verifying identities, you must treat the left side and the right side separately and work both sides to represent the same value. So you're trying to get them to be equivalent, essentially. So this technique does not prove an identity is true for all values, but only for the value of the variable being used. So, like for example, let's just look at this. It's saying we're proving that tan x is equal to sine x over cosine x for x equals 60. So we're just going to work them on the left side and the right side and prove they come to the same conclusion, which means that they are equivalent, right? Okay, so let me say that one more time. I know these are a lot of verbiage here, okay? Tan x equals sine cosine x is what we're proving. We're going to use the degree of 60 degrees to prove that these values will output the same output, which means they are the same thing, okay? So tan x, so we know what is tan of 60. Tan of 60, how I know this, guys? Remember, at 60, it's root 3 over 2 is your y, and then 1/2 is your x, right? So it'd be root 3 over 2 over 1/2. So it's just root 3. Okay? So tan of 60 is simply root 3, and we'll just stop there for the left side. That's the value of tan 60. You're going to see what I essentially just did is going to come up again. Because what is sine at 60? We're going to go sine 60 over cos 60. Well, we know it's sine. Yeah, we know sine's root 3 over 2. We know cosine's 1/2. We get root 3. So we verified that they are the same. Left side equals right side. Left side, right side, yeah. Left side, right side. That's all that means. Okay, tangent squared x plus 1 equals secant squared x plus secant squared x for pi over 6. So we're looking at pi over 6 for tangent squared and then secant squared. So what we want to do is we want to plug pi over 6 into x. So that means we're going to go tangent pi over 6. Remember, that means the whole thing is squared plus 1. So what is tangent at pi over 6? Right, it's going to be the flip of what we just did, right? So it's the 1/2 over root 3 over 2. And so that gives me the 2 still cancel. It's 1 over root 3. And so then when we rationalize, we get root 3 over 3. Okay? So tangent at pi over 6 is root 3 over 3. And we saw the plus 1 out there, yep. Okay, so watch. I'm going to go root 3 over 3 squared plus 1, which gives me 3 over 9, right? Do you guys see that? So it's 3/9, which is 1/3. Plus 1. 1/3 plus 1 equals 4/3. I'll stop there to see if there's any of the quick mental math that happened you may have got lost. So the question I'll say, does everybody see where root 3 over 3 came from? Okay, when you square root 3 over 3, you get 3 on top and 9 on the bottom. Okay, so that's why I wrote 1/3. So we're at 4/3. So now we're going to do secant squared and see what we get. Well, secant is 1 over cosine, right? Okay, so let's go ahead and look at it. So secant at pi over 6 squared. So what is cosine at pi over 6? Root 3 over 2. Okay, but we want to flip it because it's secant, right? So we want 2 over root 3. That's what secant is, correct? And now we're going to square it. Since I'm squaring it, I'm not going to. If you did, you'll still get the same answer, but I know it's going to be squared out. So when you square it, notice you get 4 over 3. Left side equals right side. So you just proved two identities. You just proved that tangent is sine over cos, if you knew that one. Maybe you didn't know the next one, though. Tangent squared x plus 1 is equal to secant squared x. That's another identity. Okay, that's a Pythagorean identity. What's that? Right, those will be on your equation sheet, yeah. Okay, so proven quotient identities of Pythagorean identities, we just did that. We can use left side versus right side. So treat the left side and the right side separately. Work until both sides represent the same expression. Do not make the mistake of assuming the answer by writing left side equals right side at the start. So they're saying is, you can't just say, you may know that tan equals sine over cos, but you need to explain why and give the left side versus right side where they simplify down. Okay. So for example, it's easy for this one to use your ratios because we know that tan theta equals y over x. When you're doing proofs in general, and good thing, I don't like proofs that much. They're a little bit more theoretical. They're interesting, they can be. But when you're ever trying to compare something, define something, you need to have something to compare it to. Okay? So like for example, when we say tan, we know is y over x our ratios, right? Well, what's sine with our ratios? Y over r, right? And then what's cosine? It's x over r, right? And so you can kind of see right here how it's going to kind of simplify quickly is that, well, y over x is what tan is. See the r's cancel? And so then you get y over x. So there's your actual proof rather than saying, well, I just know it is. Okay, so tan is equivalent to sine over cos using your ratio setup. Okay? Because the r's would cancel when you divide. Okay, cos can't be 0 for this because it's undefined. That's what they're saying here. Okay, you don't want cos to be 0 because that'd be undefined. Okay. We're going to do one more left side, right side, and then we're going to get a couple more identities where we actually kind of play around and we're trying to simplify. So we're actually almost done. Okay. Any questions so far? Okay. All right, so here we go. Use the base identities to prove the one we already did. 1 plus tangent squared a equals secant squared a. So they're just going to do left side, right side again. They wrote it the long way for left side, right side, just because there's a little bit more work here. So they're going to do left side, right side like this. Okay. So left side, so 1 plus tangent squared a. So how else can we write tangent squared a? Good. Y over x squared, right? You guys see that? So our first step, you can number them if you want. We're going to change tangent squared to y over x squared, because tangent's y over x. Remember, why are we doing this? Because we're finding ways to compare the identities. Okay? So then when we do this, that's going to be, we're just going to simplify this now. 1 plus y squared over x squared. Now here's where it gets a little bit tricky, and you got to kind of just realize that we like to get that 1 not separate, because you can see clearly on the right side, is there a 1 over there? No, so we want to try to combine this as a single fraction. So how would I do that? How would you combine those to make them a single fraction? What do you need to add fraction? Common denominator. And so the 1 needs to be x squared over x squared, right? Because I need to times x squared to top and bottom. You guys see that? And so it's just going to be 1x squared over x squared. So now this becomes x squared plus y squared over x squared. Now this is where it gets interesting. This is where you got to start thinking outside the box a little bit. We actually know within our ratios, we already actually did it earlier in this lesson, what does x squared plus y squared equal? Not 1, r squared. Because we're going to stay with variables here. Now that is where we got to. Yeah. Yep. X squared plus y squared equals r squared. So it's just kind of using what you know. Okay. Yes. Okay, so now let's look at the right side. What can we do with secant squared? So secant squared is cos flipped. So it's going to be r squared over x squared. Oh, well, that was fun. Got it. Okay. Secant squared is r over x squared. Okay, I guess I could have wrote one step, I guess. I could have wrote r over x squared for secant. And then it's r squared equals x squared, so we're equivalent. Okay, so you just proved the identity. Congratulations. Yeah, all right, woo. Okay. Couple quotient identities again. Tan x is sine over cos. Cotangent is cosine over sine. And then we just did one of the Pythagorean here. We just proved the middle one here. Okay, a couple things to keep in mind, though. Check this out. The Pythagorean comes from a lot of stuff we just did. We proved this one already. I won't talk about this one right now, but it's similar, right? Do you see it's pretty similar? Because it's a tangent with a secant and a cotangent with a cosecant. So you see the little relationship there. This one's simply, look, this one's simply y squared plus x squared is 1 squared, right? Which is the x squared plus y squared equals r squared. So that's where that one kind of comes from. So there's Pythagorean identities. But anyway.
So when you're doing this, r is still always 1?
Generally, yes. Yes, for these. But we don't have equations here. So actually, r doesn't. Yes. So, okay, yes. What you're saying, Aiden, yes. Yes. That's an r is 1, correct, for the identity. Yeah. Okay. Now, things I want you to pay attention to. Don't get locked into only looking for these patterns. Right, Bobber? Okay. We need to write these in different forms. So look what's changed. See here? I can minus the cos, and then this right here is identity for sine squared. So what I'm saying is that if you see a 1 minus cosine squared x somewhere, that's equivalent to sine squared x from this same identity. So these identities can be written in different pieces that helps you sub some stuff out or in depending on what you need. Okay, do you see that? See these two for the first one? And then you have the tan squared. You can minus the one of the secant squared. You have the cotangent squared. You can minus the one of the cosecant squared. Just different ways of looking at them. There's the same identity. Okay? All right. So let's get to a couple examples here. I don't need to read this to you right here. Let's just go. All right. So it says, express each as a single trigonometric, I can't say it today, ratio, trig ratio, we'll say trig ratio. Use graph calculator to verify. So we're going to write that as a single trig ratio. Okay, so right now there's sine squared, there's cosine squared. Okay, so we want to write that as a single. So, again, that's where you got to kind of play with it a little bit. But one thing that I noticed right away is I want to get the fractions the same. If I write as a single, I want a single fraction. Okay, that's the way I think about it. So I'm going to go cos squared x over cos squared x. Immediately I notice that's something I kind of like. Because what's the top going to have? What's that? I'm writing 1 differently, so a common denominator. So I can write a single fraction. And what I'm trying to point out is that look what's on top. Sine squared x plus cosine squared x, we like those. So we're here. Well, what does sine squared x plus cosine squared x equal? Or, according to identity, like what Aiden was asking, even easier than r, 1. Sine squared x plus cosine squared x equals 1. So this changes to a 1. You don't assume it's 1. So with the identities, it's always going to be 1. Essentially what Aiden says, that's right. Because that's what the identity is. Right. What'd you say? Oh, good idea. Okay, so Donovan just said something really good. He said, can I just write this as 1 over x squared because cosine represents x? It's a really good point, but that would be the wording's a little bit tricky here. They will actually want you to write as a trig function, so not in terms of x and y. So good idea, though. Instead, you see it's 1 over cosine, so what I immediately think about is reciprocal of cosine is what? So the answer is secant squared x. Okay. Okay. So just somebody help me out here. What would you do first to part B? Just to start simplifying this to 1 trig ratio. Change it to what? We can't do it to tangent. You mean change it to, what is cotangent? Well, it is 1 over 10, but obviously what do we have around it? I don't want tangents at all, right? Right, cos over sine. So sine x plus cos x over sine x times cos x. So I want to get them all cos and sines. Can't, because the plus sign. What's that? I can make it cos squared. Yeah, I'm going to do that next. Yep. But we can't cancel sine x. That's the problem, though, Aiden. So what's that? No, we don't want to subtract it. Good thinking. Yep. So Fo just said it. You didn't hear him? Again, we want to get it as 1 fraction, right? We're trying to write as a single trig ratio. So remember, can't talk today. Focus on getting them as single fraction. So what Fo said was, we're going to make this have a sine x on bottom. So what's that make the top? Squared. Again, we like that. Because we got a 1 up there. So it's going to be, do you guys see that it's going to be 1 over sine x? Just sine x. Yeah, it's not squared down there this time. So your answer is cosecant.
Wait, how do you get the sine squared on top?
Right. So common denominator. So what he did was sine x on bottom, sine x on top. So that one's a square now. That one's on the bottom. So you times sine x at top and bottom, just like we did here for the cosine.
Oh, okay.
So that's why the square's on top. Yeah. So if you missed this step here, I'll show it one more time. The sine x was over 1. We multiplied sine x at top and bottom to get a common denominator. So sine x squared on top, sine x on bottom. That's where that came from. Okay. Two more. Okay, so express 2 tan A over 1 plus tangent squared A in terms of sine A and cosine A and write in simplest form. Okay, so we're trying to convert this to just sines and cosines and then simplify as much as we can. So the first thing I'm going to do is I'm going to change my tangents to sine and cosines. So I'm going to go, need some space here, 2 sine A over cosine A over 1 plus sine A squared over cosine squared A. Okay, we want to get the bottom different because the bottom is 2 terms. I like it to be 1 term. So what would I do? Cos squared over cos squared, right? So I change this 1 to cosine squared A over cosine squared A so I can combine these. So then that's the next step. So it's going to be 2 sine A over cos A all over cosine squared A. That's my 1, right? Okay, now we like that because look at the top. All right, those is one fraction, which I can do, right? To the same denominator now, what's the top? 1. So now we are 2 sine A over cosine A all over 1 over cosine squared A. So now we're in a pretty good spot. So we just have fraction over fraction, right? Yep. So remember how this is going to work. We got fraction over fraction. You got underachiever here, overachiever here. Just the 2's at the top, right? Because that's 2 over 1. So it's going to be 2 sine A cosine squared A all over cosine A. Now you cancel the cosines out. And so this one goes away. That's not a 2 anymore. Your answer is 2 sine A cosine A. That's the answer. What's that? Yeah? Yeah. Because you're not sure if that's what it's supposed to look like or not? Yeah.
How do you prove it?
How do you prove what?
That that's the right answer.
Well, how can you prove it? Good question. You could plug in a value, and if you plug in that same value to that, they should be the same. Because you're simplifying, right? Yeah, just roll that. Well, no, it means you can plug in a value of, like, you can plug in, pi over 4 to this, and that decimal or whatever you get when you calculate that should be the same here. Okay, that's how you can tell. Because remember, we're simplifying. So, what's that? You could plug in 1 probably, yeah. Yeah, you can plug in 1. Except for 1. 1's not great, though, because tangent at 1 is 0. So you get 0 over 1 is 0. Yeah, you get 0 equals 0. Okay. These couple, they want us to factor now. Okay, so they want us to factor the following trig expressions. So what would you do first here? I'd take out a 3, yeah. Now let's see who can see the next piece here. Not 4th root. Good idea. So, yeah, it's the difference of squares, right? So 3 cos squared theta plus sine squared theta. Oh, that's cool because you'll see why. Why is that neat? Not both of them aren't 1. This one's 1. Essentially, that's nothing, right? Just a 1. So that's kind of like we pulled that out. That's gone. You can write a 1 there if you want. 3 times 1, that's a difference of squares again. This right here is a difference of squares again. That's your answer. 3 cosine theta minus sine theta, cosine theta plus sine theta. That's your answer. You don't have to have the 1 there. I just put the 1 there so you guys can see that it went away, but it's just a 3. Okay.
So, like, you know you're done when you just can't.
Well, you just can't do anything else.
Apply anything.
Yeah, I can't factor anymore. That's as far as I can go. I think a lot of times, Phil, like they do have questions where they'll say simplify and then plug in something to get so you get an answer. But yeah, you gotta be comfortable with that ugliness. Okay. All right. Part B, last one here. What do we want to do to go ahead and factor that? We could do that, but we don't need to do it right now. I'd wait on that. Because the first thing I want to factor, right? So if I factor this, what can I do? Take out a sine squared. They both have sine squared. So sine squared theta comes out. So look what's left. The reason I don't want you to change cotangent is because, guys, that's on our sheet. What's 1 plus cotangent squared theta? Cosecant squared. Huh. That's interesting. Why is that interesting? What's cosecant? Oh. Where the plus sign go? What? This equals this by identities. Yep. I said to go find it. 1 plus cotangent squared equals cosecant squared. Yep. Yep. Okay. Answer is 1. There you go, Phil. There's a pretty one to finish. 1. Yep. So sine squared theta we pulled out. 1 plus cotangent squared theta is cosecant squared, which is 1 over sine. So they cancel because they're the reciprocal of each other. Right here? This is sine squared theta. Yeah. Okay. All right. So that's it.